Hello and welcome to Mocana's webinar on protecting IoT endpoint devices and communications. And today we're going to talk about securing firmware updates and patches. This is one of the biggest vulnerabilities that we see within the IoT security space and industrial control devices. But it gets to the heart of how can you improve the security of updates. If that is insecure, it makes it very easy for attackers or unsuspecting employees to upload either malware or the wrong code to devices. So today we have with us Srinivas Kumar, our VP of Engineering. Welcome, Srinivas.
Hi.
Srinivas heads up our engineering team and has been involved with a number of companies. Previously, he was the CTO of Taskware, and he also spent time at SRI. He's worked at numerous companies, including Applied Identity that was acquired by Citrix, and he is, in his spare time, filing patents in the field of cybersecurity. Thanks for joining us today, Srinivas.
Thanks.
So today we want to talk about, we're just going to jump right into this. I think we all understand the basic concept of updating a device. And the device could be anything from a printer to an industrial control device to a thermostat to a surveillance camera or an industrial control system. And Srinivas, if you can talk maybe a bit about what are the different ways typically of updating a headless device, and what is a headless device?
Basically, a headless device is an embedded device in the field where there is no human interactivity possible, no keyboard, mouse, monitor. So it's basically an unattended device that has to be updated. The challenge there is how do you get the payload to that device? It can be over the air, it can be over the wire, or it could be an air-gapped device, which might require a multi-hop delivery mechanism, including possibly somebody walking up to the device with a USB stick or SD card. So that's basically what a headless device is, and the standard update methods would apply to it, such as over the air or over the wire. But in many cases, it's totally air-gapped and might require some physical access or presence.
Sure. Well, I mean, it must be, there are a number of challenges. Maybe you can talk a bit about kind of the approach in general to updates and where you see some of the challenges, and then we'll go into some examples.
Right, so the first challenge obviously is the payload has to be verified for authenticity, which has typically been done through a code signing mechanism, but with the caveat that the certificate cannot be validated, since a lot of these systems may not have connectivity to the internet. That also causes a problem of not being able to authenticate the device before giving the information to the device, especially if you're doing a pull over the air or over the wire. Trying to connect to the device over SSH or FTP has a issue of how do you actually authenticate the remote user, because a lot of these devices would not be capable of doing more reliable authentication other than perhaps a pre-shared secret or a radius auth with a password sitting on the device. And the other problem is a common practice of someone walking up to the device, bypassing the firewall, and with the physical access being able to escalate privileges, get to the root, and apply any change to the device, which could even circumvent any controls that might be on the device. So these are real world challenges of how insecure such an update would be.
We're going to dive into a little bit more on each of these, but I wanted to ask about, you talked about SSH and SFTP and FTP, and we have a number of customers companies that build IoT devices or equipment, embedded systems, and they are implementing things like SFTP over SSH. And you talked about the different methods of authentication and some being stronger than others. Can you talk a little bit about that? Like, so for example, if you're using SSH underneath SFTP, what are the different ways of authentication, and how does that impact the integrity or the security of the system?
Yeah, so SSH provides at least 3 methods of authentication that could be used. The most common practice is to use a username password, which is pretty insecure, as those username passwords have to be controlled by a policy for password management. And so that's really the first challenge. And invariably, people end up using default passwords and factory default settings and so on. The second authentication method you can use with SSH is key-based, where you would provide a key to all the devices, and that public key would be loaded up on the SSH server. The challenge with that being it's an n-square problem. It's your n devices, you got n key pairs, and how do you manage those keys? Both the practicality of providing the public keys to the server, as well as managing the security of the private key on a headless device. And the third authentication method is certificate-based, which gives you the advantage of being able to rotate those keys, renew the certificates, revoke the certificates, and so on, giving you a lot more granular control of onboarding, offboarding the device.
Sure. So, you know, some companies out there, there are many that actually just use FTP. So what I'm hearing is if you're moving to something like SFTP and using SSH, be sure you're using the strongest method of authentication. Passwords are generally easy to crack, especially with social engineering. Pre-shared keys, well, there are all sorts of vulnerabilities to the way humans manage pre-shared keys, but certificate-based authentication may provide or will provide stronger security there. Okay, so let's talk about just signature verification. So how does that work? You know, there's a board management controller, for example. This was noted in something that Eclipsium found with Supermicro servers, but pretty broadly available. These controllers weren't carrying out signature verification. Can you talk about what that is and what that means?
Sure. If the payload that is delivered to the BMC, whether it's firmware or configuration changes or OS patches, if they're not code signed by the supplier, then you really don't have a way of verifying that payload is authentic. But if it were to be signed by the supplier, the BMC code has to verify the signing. And the verifying the signing is a process that requires the public key of that PKI to be on the device. And part of the problem there is when either the private key is compromised or it's lost, stolen, then it's a challenge to update the public key on the devices. So when you get to that state where literally the device gets bricked, the only way to send an update is literally by bypassing the signature verification. So there are two problems. One is not verifying the signature, and the other is not being able to sign it and therefore bypassing the signature.
And you know, if there is no verification of the signature and the code isn't signed, then pretty much anyone can develop, customize the code, install malware, and install it in the device. The device would never know whether it's has been developed authentically or not. I was doing a search on the MITRE CVE database, and it was amazing how many situations there are like this, where devices including this, BMW's infotainment ECU on the vehicle from 2012 to 2018 on a number of their vehicles. Attackers can bypass the code signing, just as you described. And once they're in there, they could laterally attack other modules and ECUs for drivetrain or navigation on the device. How about, we talked about insecure FTP. I think this is pretty self-explanatory, but why would companies just implement FTP on a device as a way to update or move files?
Well, in the past, companies have used SSH and FTP as a way to transfer files, purely because they didn't have either a web stack on the device that could do a pull. So it was pretty much a push mechanism. And even if there was a pull where you have a SSH client or a FTP client sitting on the device and it would go and pull it, it's pretty much just for the purpose of doing a file transfer. And a file transfer is not really a process, it's just a method to move the file. You have to build protection above that transport protocol. And so using authentication as a means to initiate that transport protocol is not really end-to-end security. You're only securing the FTP connection on the wire, but in terms of validation of the content that came through on that SSH or FTP session, that's where the gap is. You could securely transfer malware to the device. So it's not a matter of transport security. It's a matter of content security before and after it gets into the transport.
Right. So really, with SSH, SFTP, a lot of these elements, you end up securing the transport with FTP over SSH, for example, but not the payload itself.
Right.
Privilege escalation. This was one that was just reported actually pretty recently, that a number of these network devices, and we've seen this across the board with routers and switches that have been reported to be vulnerable, seen that in the Shodan database very broadly. Talk about privilege escalation and how attackers use that to begin to remotely update applications and firmware on devices.
Yeah, I mean, there are various methods that attackers have typically used for privilege escalation, all the way from remote code injection to vulnerabilities in the SSH client or server. So this is basically being able to get to a root access which bypasses access controls. And once you get to the shell and are able to operate as a super user, you can pretty much tamper with any component on the device. And since a lot of these devices don't really have a lot of host-based intrusion detection or tight controls like a typical IT system would have, it would be pretty easy for an attacker to get to that privilege escalation. It can either be coming in through a Wi-Fi interface or coming in literally physical with a USB stick.
So lots of ways to update devices insecurely. Let's start shifting to what we can do to change that. And I think that there are certain fixes, but it's also a broader problem about the whole supply chain. Can you talk about what goes into thinking about, or how updates are dependent on the different components of the supply chain, from designing the devices and securing them to manufacturing them and activating them or enrolling them all the way through to update? Can you talk a little bit about what companies should think about, especially manufacturers of devices?
Right. So the supply chain integrity really starts with the first time onboarding of the device, where the device has some kind of a silicon-based root of trust or software or firmware-based root of trust at the development stage. And then through the manufacturing process, that gets onto a OEM platform and then gets shipped to the end user, where the device is activated for the first time. During the first time activation of the device, that device needs to be authenticated for genuineness, that verifies the integrity of the root of trust itself, and then verifies that that valid root of trust is an anchor on that platform. And then based on that, generate a certificate for that device as part of activation of the device. Now that certificate becomes the basis for the device to now reach back to a supplier, saying, I have landed and I am a genuine device and I've been accepted and owned by an entity, and here's a certificate issued to me by that entity saying that I am a genuine device in their network. And then that now becomes the basis for that device to reach out to an update management system, whether it's a device management service or a third-party service provider, to pull updates based on its certificate. So the supply chain here comes in as a full cycle. First, the device has to land and prove that it is a genuine device. Then it gets a certificate that qualifies it to get an update. And then the next cycle of that is when the update is received from the update management system. The update management system has to now qualify itself as an authentic provider of updates. Mm-hmm. And so through the supply chain, the supplier and the publisher must also sign and attest to the genuineness of the content. The content has to come through a supply chain that's verified. The device has to be authentic, and then the connection happens and the genuine content is given to the genuine device.
Right. You know, I mean, the fact is that so many cryptographic controls and processes depend on a strong root of trust as the basis for authentication and the creation of digital certificates. What I'm hearing is you have to start there to ensure that the certificates that you're using are rooted on something that you trust. And if you don't do that in your design and manufacturing and activation process, then it will be easier down the road for people to compromise anything. Man-in-the-middle attacks, stealing private keys, that can then be used down the road for things like update or management of the device or accessing it. So start there first, and as you move into actually how you update it or manage those different components, let's talk about how Mocana helps with that. At a very high level, can you describe TrustPoint and Trust Center and how those can help to secure the device, and then also help with this, both the certificate provisioning and management and updates?
So the life cycle of the device, as we said in the earlier slide, starts with enrollment. That's the onboarding of the device. So at first power on, the device uses the enrollment client to authenticate itself to the enrollment service that it homes in on. And once it is authenticated, it identifies itself with a proof of possession of a secret associated with its identity. And then the enrollment service issues a certificate back to the device based on a policy that is configured on the enrollment service for that device based on its authentication and identity. And now the EST protocol, which is enrollment over secure transport, is used to issue a certificate to that device in a way that only that genuine root of trust will be able to receive that certificate because it's sent encrypted. So that comes step of inducting the device, onboarding the device into a device management system. And now that certificate becomes the basis for an update client on the device that reaches out to the configured update service and identifies itself by its profile, by its attributes, which allows the update service to provide a policy-based update package back to the device. And the device then can validate the complete supply chain provenance of that update package and apply that update on the device. So that's basically what the enrollment and update clients do with the companion enrollment and update service running in Trust Center.
Got it. I mean, that automation of enrollment is kind of a big deal, right? We have a lot of customers, I would say the majority of companies out there, that use very manual processes to provision certificates to devices. There's an ID on there, but provisioning or using keys, provisioning keys or pre-shared keys to devices, requesting certificates, oftentimes that is done by an admin, a human, and that manual process puts that person in the position of being able to see private keys that they could end up selling to someone else or compromising the device by enabling someone else to get access to those. And that manual process is a huge problem in the supply chain. And this enrollment client and service that automates that eliminates many ways that a person could get access to those private keys, which should really only be known by the device itself, is a huge step up in security. And that allows you to have a trustworthy certificate on the device on which to build the update service. So let's talk a little bit about the update service and TrustPoint. So TrustPoint is Mocana's software that is typically deployed on gateways, endpoint devices, IoT devices, industrial controllers. TrustPoint is on about 100 million devices today by many of the largest industrial and IoT companies, and it is designed to integrate across 70 plus chipsets and 30 RTOSs, highly portable. And that forms the basis to make that device tamper resistant. And as Srinivas described, the enrollment client and update client enable you to remotely or to automate the enrollment of that device, as well as automate and secure the updates. So let's dive into kind of the update itself. And you've talked about it before, but can you go over some of the high-level elements of our update solution?
Sure. So the update mechanism that we provide from Trust Center includes 4 core aspects. One is a mutual authentication that happens between the device and the Trust Center update service, in a way that for every update, the genuineness of the device is validated, and similarly, the device can validate that it is talking to a trusted Trust Center service. The second aspect of the update package is that the package contents have to be signed across the supply chain in a way that all the way from the developer to the provider to the publisher, they all have signatures, which allows for what we call as a multi-factor verification that happens on the client. The client, when it receives a package, looks for all signatories and verifies all signatories which means throughout the supply chain on every hop, tamper resistance is guaranteed. So at no point from the time that, let's say, the firmware leaves the developer through that organization that is providing the software update to the distributors and to the publisher who actually owns the device, at no point can any tampering happen in flight or at rest. The package is always encrypted and always signed at rest and in transit. And the package itself is delivered as a full PKCS 7 compliant envelope, which is basically an open standards approach in a way that all the signer certificates can all be bundled into that PKCS 7, which makes it easy to configure, manage the life cycle of associated certificates.
Right, and being able to verify the code, multiple signers, and the package itself that's used for delivery is a meaningful improvement in the way updates are handled. It goes beyond FTP, SFTP over SSH for sure, or simple hash and sign with a common public key on a device that that companies often use for validating updates. The stack that is used to develop or to deliver this is a core piece of what we do. So Mocana TrustPoint is embedded security software that companies can use on the device. It includes source code and binaries such as the enrollment and update clients. And it's very comprehensive, highly portable to multiple operating systems and hardware platforms. And it does much more than just updates. It ensures device and data integrity. It uses a FIPS validated crypto engine with on-device certificate and key management. And it also supports a broad set of protocols, network protocols, all standards-based authentication protocols like PKI, IKE, and EAP. It's a very comprehensive development framework and for the device. Now, Trust Center, as we talked about, really completes that by enabling you to manage it. Maybe we can talk a little bit about how that code and package signing works with PKCS and Trust Center. Giving an example of, this is a very typical example of a supply chain. You know, you have a software developer and they want to implement an update for an ECU. Let's say it's an infotainment ECU on a car, and on a BMW, that you want to verify that code is actually trusted. Can you step us through the roles of that supplier and what we call provider and publishers?
Yeah, sure. The software supplier is where the trust center for the provider is, which is basically a role that is the originator of the content. There can be multiple providers providing various updates. It could be a silicon vendor providing a firmware update. It could be an OS vendor providing an OS patch. It could be a managed security services provider providing a configuration update, and so on. That update basically goes all the way to the OEMs. It can go to the publisher. The publisher is basically the entity that owns the device, right? So the software supplier does not have information about where the devices are. They just know what type of devices, what vendors, what categories of devices the updates are intended for. And so that passes through the supply chain down to either the system integrator or to the publisher. So in the case of an automobile, it could be an entity that provides the software for the ECU. Then there's the ECU manufacturer who gives it to the automaker, let's say the Toyotas, the BMWs, who give it to the dealerships, who send it to the local dealerships within the state. And eventually your car gets that update through the dealer. So there's a long hop and multi-hop of how it got from the developer to your car. And at every point, every entity would have signed the content, and so you know that the content as developed by the developer was not modified.
Right, and the ECU has effectively the public keys associated with each of the signers, and as it receives that PKCS7 envelope, it can verify the package and then all of the signers before it installs it.
Right. So in every hop year, the software supplier here signs the package using their private key and encrypts it using the certificate of the ECU manufacturer. The ECU manufacturer can therefore verify that the package was intended just for them, and then they co-sign it with their certificate and forward it to the auto manufacturer. The auto manufacturer now verifies that there are two signatories and that package was signed only for that automaker, encrypted for that automaker. And then that chain continues. So by the time the vehicle receives it, it should see 4 signatories, and it should see the package encrypted by the dealership using the certificate of the vehicle. So it's almost a very personalized drop from the developer to that vehicle in a way that along the chain, no tampering was possible.
Right. Excellent. Well, that is the way to do it. And this begins to solve some of these problems we talked about earlier, right? One, being able to think about the development of the device and the security from the beginning of designing the device. And then making sure that you are implementing and provisioning identities and certificates to that device securely so that those are trusted. And then as you activate it and update and manage that device, we're recommending that you use some of the strongest standards out there with multi-factor verification, code signing, PKCS standards to ensure that updates are secure, and especially for mission critical devices, it's a critically important step to take in designing the process and designing the device itself. As we mentioned earlier, the way you leverage this is by leveraging Mocana software on the device and with Trust Center in a private public cloud or on server infrastructure. But it's pretty simple. We'll provide you with the code and the binaries that compiles in with your application and is pushed in as a binary or a set of libraries within the application as a firmware update for the device. And we work across a variety of chipsets and operating systems, and not just Windows and Linux, but also a variety of real-time operating systems, QNX, FreeRTOS, VxWorks, etc. And there are various ways of leveraging Mocana for devices that are as small as a sensor on up to server class systems or integrated systems in large ICS environments. I want to talk a little bit about what happens when you really start to adopt some of these recommendations, and how what we're talking about can actually defend against 3 attack vectors that we see that network and layered network defenses don't really address. So starting first with the physical attacks and lateral attacks. Can you talk a little bit about physical or lateral attacks that and how we protect against some of those
Well, the physical attacks can happen either through USB stick, for example, or in a way that somebody can actually get physically onto the device. And then there's the sophisticated attacker who can do side channel attacks and so on, literally getting down to the level of electron microscope, if you will. So the way we support those type of protections is by integration with the silicon vendors. And a lot of the silicon vendors, TPM as an example, they provide the cryptographic boundary within the silicon, which makes it relatively harder to do side channel attacks, as well as steal information out of the silicon. So that's basically the physical protection enabled through our integration with silicon vendors, the secure elements that are available on the market. The man-in-the-middle attack is typically either browser-based SSL exploits, very standard exploits that you're aware of. So our SSL stack has gone through all the independent testing to qualify, make sure there's no exposures based on the way attacks can happen either through the SSL engine or through the crypto engine. And obviously, if it's a browser-based attack, the browsers have to be updated and be on the latest versions. We support the latest versions of TLS and do our testing to make sure we're not vulnerable to the common attacks, exploits of SSL engines or crypto. Crypto goes through a FIPS 140-2 level 1 certification through NIST, and so that's how we try to mitigate potential man-in-the-middle attacks. The insider threats can come through supply chain, the bad actor, and that's where the signing process, where we implement a minimum 3-person rule. 3 different people have to be involved in the signing process, which makes it relatively hard for a single bad actor to inject any malicious content all the way from a developer to a distributor to publishers.
That's great. Thank you. We have a question here from the audience. How can flash memory, whether embedded or discrete, assist in cybersecurity, whether based on Mocana tools or not? So how can flash memory assist in cyber security?
Well, there are 2 ways. One way is to use the flash memory with some kind of policy-based access to store keys and certificates. You take a data flash portion of the flash and with some kind of policy authorization, have the ability to store keys and certs in a data flash. And that would require some kind of device fingerprinting to protect it with some symmetric key. The other emerging solution that some silicon vendors you're working with can provide is an encrypted flash file system. So the flash itself is encrypted by the silicon vendor, providing for one additional layer of protection. So it's really as a key store or a certificate store that flash comes in handy.
Mm-hmm. Mm-hmm. That's great. Thank you. So that takes us to the conclusion of the slides at least that we had. And if you don't know much about Mocana, we're a provider of embedded security software and security lifecycle management solutions. We've been around for a while, since 2002, and we serve some of the largest industrial manufacturers and OEMs and device manufacturers in the world. We're on about 100 million devices, helping to make them tamper resistant and protecting critical infrastructure. If you do have any other questions, I see a couple coming in here. Please feel free to log them in via the chat. And one question we have here, Srinivas, is around the partners that we have, and what we're doing specifically with the root of trust on and secure boot on different silicon vendor platforms. Can you talk a little bit about that and how that fits in?
Yeah, so we provide integration with various silicon vendors in terms of the crypto functionalities, the trusted functions, and root of trust services that are provided, like TPMs, ST-Safe, Atmel, chipsets, NXP, and so on. So we are also supporting MIMS. So any secure element that can provide secure key storage, an enclave for operations that can be performed in terms of PKI. And a lot of times it's really as a key wrapper key to protect the keys because on these headless devices, you really can't depend on keys being protected on a file system that's not secure. We also provide enhanced secure boot, which is called cyber boot, where we integrate with the first stage bootloader. We do it in a way that we can support UEFI boot as well as Flashbased boot. And that basically hardens the device from power on and then allows us to do the device fingerprinting to provide, like someone just asked, flash-based protection. So it's a cascade effect of making sure the boot was verifiable. There's no rootkit or bootkit on the platform, and then that becomes the basis to trust a in-memory symmetric key generation, and then leveraging the secure element to protect the artifacts like keys using that symmetric key. So it's a combination of secure boot, device fingerprinting to generate a wrapper key, and using the secure element to protect the keys at rest.
Great. Thank you, Srinivas. I do want to remind everyone that we have another webinar coming up on October 3rd. We hope you'll join us. It's on automated security lifecycle management, specifically about leveraging Mocana Trust Center to automate certificate management. We have one more question here. Example of a smart city security solution, what and how? So edge devices, HVAC controllers, or smart grid. Could you give some examples of where Mocana is deployed?
We're deployed pretty much across networking equipment all the way from access points, switches, and routers on the networking side to devices, sensors and actuators, whether it's thermostats, and so on. We are also on gateway-grade devices, TPM-based gateways, which form the edge computing infrastructure for fog. And we are also in containerized environments. We support Docker, LXC, Alpine kind of containers. And so we're also in those type of devices that require edge computing.
Yes, absolutely. We're implemented across industrial, both discrete and process manufacturing, industrial control equipment, aerospace and defense controllers for avionics, healthcare and medical equipment, and also transportation equipment, locomotives and automotive, and also a variety of IoT devices. So, yes, please call us, and we would love to work with you or help you think through your own security strategy when it comes to scaling or simplifying or securing your own strategy. And with that, I want to thank you, Srinivas. Thanks for joining us today, and we hope you will come and join us again at a future webinar for those of you on the call. Thank you very much, and have a great rest of the day and week.